this is Tyler. Tyler McMullen is CTO at Fastly, where he's responsible for the system architecture and leads the company's technology vision. As part of the founding team, Tyler built the first versions of Fastly's instant purging system, API, and real-time analytics. Before Fastly, Tyler worked on text analytics and recommendations of Scribd. A self-described technology curmudgeon, he has experience in everything from web design to kernel development and loads all of it, especially distributed systems. Tyler brushes his hair 100 times every night to keep it looking this magnificent. Let's give it up for Tyler. Do it.
There was supposed to be a fake thing in there. Okay, so I only have 15 minutes, so I am going to spare 0 time for pleasantries. So how many people here either know about or have heard about CRDTs? So like most of the room. Awesome. How many of you have actually built real production systems using them? Far fewer of you. I know you did, yeah. So why the difference there? Well, from my perspective, I think there's like 2 primary things with that. The first is that they're seen as like really complex or theoretical. It can be difficult to figure out how exactly you would apply these to a real system sometimes. And the second thing, once you've gotten past that, is dealing with the performance problems associated. So in this like little tiny talk, we will try to address both of those things. First, the former one. Okay, but first, actually, let's go over like a real quick review for those who are not super familiar with this stuff. All right, so lattices. Sorry, I know. Real quick. So it's a data structure. It's a mathematical concept. Specifically, what we are talking about in this case is what is called a joined semilattice. Ultimately, what that means is that for any 2 instances of this thing, of this data structure, there is a function, a least upper bound, a join, or a merge. Those kind of all mean the same thing, a merge function, so that regardless of how much they have diverged from each other and how much time has passed between them, they can always be merged back together somehow, right? So that's kind of what, like a CRDT is a type of lattice, essentially. So if I were to do a diagram of this, it might look something like this. So you start from a root, and then from that root, from that bottom value, they can diverge, right? So this might be, you might look at this like a map data structure, right? Like one node decides to add A, another decides to add B, another decides to add C, right? So at this point, these have diverged, right? And then based on the fact that these are on a lattice, we can always merge those back together. So if we had A, B, and C, in this case, we're merging A and B back together. Now we have a data structure that has A and B, right? And regardless of how much time has passed and what order you merge them in, they can always be merged back together and then diverge again, right? Okay, so let's talk about causality. So lattices are really useful for modeling causality. Specifically, version vectors are something that counts as a lattice and models causality. So version vectors. In this case, we have what's called a space-time diagram. So we have 3 servers, 1, 2, and 3 across the sides, and we have time going across, right? Or going across, I don't know. Cool. So we can see that like when S1 has some sort of event, it modifies itself in some way, it mutates in some way, it increments its own element of that version vector, of that vector. So S1 modifies the first element, right? So now it's 1, 0, 0 from S1's perspective. S1 might replicate that over to S2, and now, okay, S2 sees 1, 0, 0. Great. So at this point, things could start to diverge, right? So at this point, S3 modifies itself, okay, and that's 0, 0, 1. So 0, 0, 1 is interesting because if you look at like the state of S1 at this point, 1, 0, 0, and you look at S3, 0, 0, 1, those 2 things are neither before or after each other. They are concurrent with each other. Neither of them is before or after, right? Whereas with S2, we see that it has modified itself, but it still has S1's state in there. So S1's 1, 0, 0 state strictly happened before. That happened before relationship is important for this. Okay. And so we continue to like, and the whole idea is that we continue to merge these together over time. Great. So CRDTs. How many people are familiar with that one? All right, a few of you. Good. So CVRDTs, or otherwise known as a state-based CRDT, are like a self-contained data structure, right? So this includes like the data that you're putting in, like maybe it's a map of some kind, so you have your keys, your values, but it also contains the causal context for that, which lets you do the thing that we were just describing, where you can merge them together in any order and it doesn't really matter, right? So that's CVRDTs are a state-based CRDT. Then you have CMRDTs, which are an operations-based CRDT. I swear, we're almost done with the review. The idea with CMRDTs is that rather than composing a data structure that has all of the causal context, all of the like actual data that you're talking about, what you do is you actually replicate individual operations. Instead of replicating the whole thing, you replicate like, oh, I wrote 1, oh, I wrote 2, whatever. The interesting thing about this is that you have to deliver those operations in causal order, right? So in other words, if I say, oh, okay, I wrote 1 and then I wrote 2, I would have to deliver that to another node as I wrote 1 and then I wrote 2. I wouldn't be able to say I wrote 2 and then I wrote 1. They would diverge. Right. So the neat thing about this is that it's a smaller data structure size than the state-based, primarily because you have like offloaded all the causality like problems, all the causal context to the messaging layer itself. They also tend to be like much simpler to implement, again, because you have moved a lot of the complexity off to like the messaging layer. Okay, cool. Let's talk about the problems of this. CVRDTs have a large communication overhead. The problem with them is that in order for you to be able to maintain this constraint of saying like, oh, okay, I can merge any of these together at any point in any order, you have to like actually replicate the entire data structure, the entire damn thing, right? In addition to like the huge communication overhead from that, you also get like the merging large data structures together can take some time as well. All right, so that's that problem. See, MRDTs have a different set of problems. The causal ordered message layer can at times require like buffering large numbers of operations. So you can essentially like if you have network splits, for instance, you can end up having to buffer huge amounts of data so you don't have that like consistency that you might be looking for. Additionally, you have to execute all of those operations one at a time, right? So even if you batch them all together, if you're doing a huge number of operations, you actually have to execute them 1, 2, 3, 4, all in a row on every node. This can be a problem. So if you're interested in that kind of stuff, this is a master's thesis that just came out last year out of the University of Lisbon, dynamic adaptation of geo-replicated CRDTs, and it actually has a really great description of the trade-offs, as well as like really comprehensive performance reports on this. So pretty cool. Great. Now I finally get to talk about little delta CRDTs. All right. So delta CRDTs were introduced in this paper. Then they were further developed in this paper. This one is kind of cool because it comes along with like a catalog of data structures. So the people who worked on this actually like implemented a whole bunch of them, at least in theory, and like they show you how to actually like walk through it. So it's a longer paper. The idea behind delta state CRDTs is that you want to get like small incremental messages like operations-based CRDTs, but disseminate them over unreliable broadcast layers, like state-based CRDTs. So how do you do that? Well, the goal is described in the paper as to ship a representation of the effect of recent operations while maintaining the idempotent nature of the join function. So that sounds kind of similar to like operations-based, right? So we're shipping, it sounds like we're shipping the operations, but like the key word there is the effect, right? So we're not actually shipping the operations, we're shipping the effect of the operations. So what does that mean? Well, the core idea of this paper comes down to this thing called a delta mutator. By the way, I promise that the second half of this talk is going to be like much like less Greek letters. So each delta CRDT defines a set of delta mutators that correspond to each update operation on the data structure. So in the case of like a counter, you might have like increment and decrement. Those would be two delta mutators. In the case of a hash map, you might have like insert. Cool. So if we take our delta mutator and apply it to our current state, delta mutator, current state, then we get a delta. And that delta is the thing that's supposed to be the representation of the effect of that operation. So it's not the operation itself, it's the effect of the operation. I know it's very fucking vague. It's fine. Just go with me. So then if we take our old state and we join it with the result of our delta mutator, aka the delta that we just saw, then you get a new state, right? So the idea here is that operations are not actually applied directly to the data structure. Instead, we generate a delta, and then you join that delta with your current state in order to produce a new state. So what that means is that if you can do that, you can actually join that delta with other data structures and produce the same state, right? So further, it goes on. So if we have multiple deltas, we can join those together to create what's called a delta group. Delta, delta, delta group. And then finally, if you were to say, take our old state, join it with the delta group, and we get a new state. And that new state should be the old state, but with all of the effects of all of the deltas that you merge together to create that delta group. Okay, so it's that delta group that we actually ship to other servers. That thing is supposed to be the representation of recent operations that I mentioned earlier, right? So the whole idea with delta state CRDTs, little delta state CRDTs, is that we build up these delta groups and then we occasionally distribute them. It's actually a lot more complicated than that, but this is a 15-minute talk, so bear with me. So that's kind of the core of the delta CRDT idea. It's essentially like the interface or the constraints that a data structure has to match in order to make this work. If this were a 45-minute talk, I would show examples of like how these implementations actually happen, but it's 15 minutes, so let's move on. Enough about little delta CRDTs. Let's talk about the more interesting, or more interesting in some ways, big delta CRDTs. So this paper was released last year. It's 3 pages long. It was released at a workshop, not at a large conference or anything like that. It was by the students of someone who was actually working on delta CRDTs, the student of the people who did the previous one. But I actually really like papers like that because they usually introduce a small idea that simplifies things, and that's exactly the case in this one. So basically, they took the idea of the primary, the little delta CRDTs and simplified it. So in my opinion, given the fact that so many people here have heard about CRDTs but never actually used them, this paper is probably the easiest way to get your foot in the door to make this work. It's actually simplifies the whole thing by quite a lot. It has serious limitations, but it's a good start. Also, I really enjoy the shade that they threw into the title. So the whole idea with yeah, I think they're actually already in there. Yeah. So the whole, the key difference between little delta and big delta CRDTs is that little deltas build up these delta groups in response to each operation. But that ends up complicating the communication layer. It makes the whole thing a whole hell of a lot more complicated. A simpler way to do this would be to generate deltas on the fly when someone asks you for a delta, right? So remember that we have that causal context associated with each one of our CRDT instances. So if we can find a way to say, oh, here is my current point in time with my version vector or whatever that is. What is your point in time? Send me the difference between you and me. Okay? So how would we do that? Well, it looks like this. When one node wants to exchange state with another, we send a version, which in most cases, in the case of the actual paper, they're talking about version vectors, again, just like we were talking about earlier. Cool. So it's basically just a way of summarizing the causal time. It is at this point in the history of this data structure that my current state is. So when that other node receives it, it generates a delta and sends it back. What it does is it compares its own version to that version it just received and constructs a delta of everything that it knows about, everything that has happened after or concurrent with the version that it received from the other node. Yeah. So at that point, the first node gets it and it merges it. Much, much simpler than the other one. The paper actually describes it like this. I've grayed out the bits that are not relevant, but it's actually exactly the same thing that I just described. You periodically decide on a random replica, you send it your version vector. When you receive a version vector, you get a delta, you send it back, then you merge it, and that's it. Cool. Let's talk about an example. This is kind of stripped from a project that we had going on inside Fastly that we were working on, and if you want to hear more about that afterward, I would be happy to talk about it, but at the moment, I will just kind of summarize it. So this project was written in Go, and man, with the complexity of CRDTs, you might expect the actual data structures associated with this to be kind of gnarly, but it's not. It's really easy. So you have a shared map that we're going to try to replicate across all of the nodes. We have our storage, which is just a map. We have our key, points to a shared map record, and you keep a version vector alongside that. In that shared map record, you keep your value, of course, and you also keep what's called a version vector dot. So whereas like a version vector kind of represents like, oh, okay, this is my point in time. Everything, like, I know exactly where I am compared to everything else. This is what I know. Like, it represents that point as well as everything below it. A version vector dot represents just that one event. Version vector dot is essentially just like node and version, like number, right? So it's just like two pieces. So here's how we do it. I'm going to use pseudocode. So we send our version vector. That's the first step. Really easy. Yeah, we literally just turn it into JSON. It's fine. So when we receive a version, what we do is we iterate through it iterates through its own CRDT map. And for each record in their map, we say, okay, so I got this version from my peer. Is that version, did that version happen before this record, or is it concurrent with this record? If either of those statements are true, then it will add that to the delta. So essentially, it adds everything that those did not come before, essentially, which is actually pretty straightforward with version vectors. And then we add our own version vector to the delta, and we send it back. Great. Super easy. It's only a little bit trickier when we actually have to do the merging, right? So we receive a delta. We go through each record in the delta. And if the dot associated with the record that we received happened before our version vector, then we skipped it, because we know that it happened before. It was like, it's old. We don't care about it, right? Then we look at our record. And we say, OK, is our record, did that happen before the version that we just received? Well, then the one that they sent us must actually be newer, right? So then we merge it. And if they're concurrent, then you do business logic magic, and it's fine. Right. So no, literally, it's just like you actually have to. In this case, we're talking about like what's called a CRDT register. So it's really just like business logic. You decide like what it actually means for things to be concurrent. Right. Caveats. So things that are different about this from regular CRDTs. This assumes that you are doing a pool-based gossip system, which has like significantly different characteristics than a push-based gossip system, which is fine. You know, you should just know that. Additionally, generating the deltas for this can actually become really expensive over time. And thank you. That was the quickest introduction to that.
Right, this is Kevin, our next speaker, and then I'm going to tell you things about him. Kevin likes building great experiences. He helps scale Twilio and Ship, and currently runs a software consultancy. Kevin once accidentally left waiting for Godot at the intermission because he really needed a burrito. Kevin's favorite song is Delilah by Tom Jones, and he does a mean rendition of it in karaoke. Let's give it up for Kevin.
Thanks, Inez. If the talk goes sideways, we can just put on Delilah, and I'll just start singing in the middle of the... All right, so I'm going to be talking... Thanks for coming, everyone. I'm really excited to be here. I'm going to be talking about public key cryptography, and in particular, this one implementation of public key cryptography called Curve25519. And we're going to kind of work our way up from first principles. So what is cryptography? That's a good kind of starting question. Basically sending messages without someone in the middle being able to read them. So one of the assumptions of cryptography is that an attacker can read the text that you're trying to send to someone. Like, imagine I'm trying to send a message to someone who's in the back row, but I can't text them or anything. Like, I have to talk to them, right? And so you can all hear what we're saying. I don't want you to be able to understand what we're talking about, right? So I have to encrypt the communication in some way, right? And this is broadly true across eras, across technologies. Wi-Fi, you can read Wi-Fi packets, right? Which is why so much of the internet is moving to HTTPS. Radio in war areas, this is a big problem. A lot of communications go over radio that can be intercepted. If you send a message with a messenger, something stopping someone from harassing that messenger and trying to open their secret briefcase or something and read the message. So you need to have better encryption on top of that. So the middleman, they might try to intercept the message, they might also try to forge messages, right? And we want to be safe against that too. We don't want to have someone being able to fake messages that the other person thinks is real. And if the person tampers with it, like let's say they read the message and swap out a keyword in the middle, we want to be able to know that that happened, because that would also be bad. Okay, this is not steganography. So steganography is hiding messages in places that people don't think to look. They're generally not encrypted, they're just kind of hidden, and so you have to know where to look to decrypt, to find them, right? To find the message, and that's kind of a different branch, but it's neat. So the prototypical example of this is grape juice. You write a message in baking soda on a sheet of paper, and it's invisible, and then someone puts grape juice on it, and the invisible text becomes visible. You might have done this as a kid. But this is another fun example. Well, fun. This was a U.S. soldier who was captured by the Vietnamese in the Vietnam War, and the Vietnamese wanted to do a video where they said, show the U.S. that you're being treated fairly and that you're still alive. And he, under the pretext of that there were really bright lights, blinked out the word torture in Morse code. This was actually the first evidence that the United States had that the soldiers were getting tortured in Vietnam. Okay, so moving up a bit. Symmetric cryptography is a form of cryptography, which is separate from public key cryptography. The idea behind symmetric cryptography is we take a message and we transform it. We send that transformed message to the other person, then they reverse the transformation, and then they read the message, right? This usually involves some kind of secret key, right, that you have to negotiate with the other person before sending the message. So here's an example. ROT13, this is like the easiest possible example. Let's say I have a secret message that I want to send to someone. What I do is I take every letter and I either add or subtract 13 letters from it, and then the counterparty does the same. So since the alphabet is 26 letters, it doesn't matter which way you go, it works. So then you would send this, and then you would decrypt it by adding or subtracting 13 from each one. So the key in this is 13 letters, right? Like that's the secret key. The next example, shared text. So let's say we agree to use a shared text for doing encryption, right? So in this case, let's say we agree to use the Constitution as our shared text. So I start with my message, Omar, come in, and then I write immediately below it, I write the shared text, so the preamble of the Constitution, we the people, and then I add, right? So O plus W gives me a large number. If you go above Z or above 26, you subtract 26. In this case, you get K, and so on and so forth. Does this make sense? Does everyone kind of understand the adding? Okay. So then you send that encrypted text, right? And so as long as someone doesn't know what shared text you're using or can't guess it, this is pretty safe, right? It turns out that English is not actually a great shared text because there are a lot of really common words. Like you might guess they're using the word the, and so you just kind of move the word the along the text and see if the resulting text makes any sense. So English is not a great fit, but if you want to do really simple stuff or beat the camp counselor or something, you can try this. Okay, so then decrypting works exactly the same in reverse. So you start with the encrypted text, use the same text, subtract it, and you get the secret message. Who knows what this is? Someone want to say it? It's an Enigma machine. So yeah, so this is the machine used by the Germans to encrypt messages. It was famously broken. A very simple example of how this works with 3 letters. So there are 3 dials. Other versions had different numbers of dials. This is extremely simplified. There are 3 dials, and you send a message, and it goes through each one of those dials. And the dials have letters on them in a random order. So the first letter of our message is O, goes to the first dial. We add D to it. Second dial, we add H. Third dial, we add U. We get S. We send S over to the other person. When they get the message, they have a way to reverse it, they type in S, and then O comes back out. So the key to the enigma was each letter you advance the dials by 1. So in this case, we start with DNT in the first dial. Now we've typed one letter. Now M is the top letter, right? So now we have a different key for encryption. If we keep going, the dials go to the third position. And then once we reset the first dial, this dial number 2 advances by 1, right? So they had up to 5 dials at one point. Each dial has 26 positions. You can encrypt a large message. And so the way that they would do this is they'd send around these books that would say, here's today's dial settings, right? So you just initialize it to the starting position, start sending out messages, right? So obviously for the Allies, capturing the books that had those in settings was really important, but then also they had a whole bunch of tricks to try to break it. So they knew that like a weather report would go out really early, and so they try to search for the word weather in the encrypted text and check different dial settings. This is probably the last like brute forcible, widely used encrypting cipher in 1945, or 1944, 1945. Since then, there's been better algorithms developed. Okay, so another example of a shared key is a one-time pad. So I just generate random letters. You can use a variety of different sources for this. Radiation, like radiation's a good one. The least significant digits of like you typing is another good one. There's a few different ones, but basically you find some random source of data and you just generate random text. And then you have to send it to the counterparty, right? So you have some way of securely getting them this one-time pad, and then you say use one-time pad number 7, and then they fetch out one-time pad number 7 and use this to decrypt, right? This is perfect decryption, assuming that you have a way to get that one-time pad to the other person, right? You can't decrypt it because it's just random. There's no pattern or anything. It doesn't compress well, right? So here's another example from World War II where this is how the Allied commanders would communicate with each other, called this system called SIG-SALLY. And what they would do is they would take random data and encode it onto 12-minute long, like golden records of just white noise. And then they would send those across the Atlantic. So then when Eisenhower wanted to get on the phone to Churchill, they would synchronize exactly the record's start times and then start playing them. So Eisenhower would talk. The system would add the white noise to Eisenhower's voice. And then you'd get this encrypted noise. It just sounded like white noise. That would get sent over the Atlantic. And then in England, they would do the exact opposite. They'd take the secret noise. They would subtract out the white noise because they synchronized it very carefully. And then you'd end up with the decrypted voice at the end of that. So that's an example of one-time pad. It was totally random data due on a record. After the end of the call, you destroy the records. And so that's how they were able to talk without having it being able to be broken.
Did they reuse that pad?
No. I mean, no. Okay, so nowadays, what do people use for symmetric encryption? They use things called stream ciphers. There's a lot of fancy math involved. Usually involves doing transformations that sort of hide the source of the message. This is 5 lines of this stream cipher called Salsa 20, which you may have seen as part of the libsodium or NACL set of libraries. But yeah, so you just do this for a bunch of rounds, and then it sufficiently obscures the message that it's hard to kind of reverse out the key if you don't know the secret key attached to the message. That was used to encrypt the message. So what are the inputs for a stream cipher? So you have a 32-byte secret key. You have a 24-byte nonce, which I will explain in a little bit. Then you have a 64-byte block counter, which is you start the counter at 0. After you encrypt 64 bytes, you increment the counter by 1, and then you re-encrypt the next 64 bytes with that new counter, right? And the way you kind of smash these together is such that each 64 bytes that you encrypt is unique, because this counter is changing every 64 bytes. So So the secret key is just like random data, right? Like it's the same atmospheric randomness or random data. A nonce, I will get into in a sec. I just explained. So what is a nonce? A nonce is designed to make sure that each cryptographic, like the ciphertext, like not even the message, but the ciphertext they're using to encrypt, like remember that like we the people example or the one-time pad. If you didn't have a nonce, you'd get the same exact one-time pad from the same secret key every single time. So this might be easiest to imagine with Sig-Sally, right? Imagine that they reused the record, and there was someone in the middle that was recording the encrypted white noise, right? So Eisenhower gets on, he makes a call. We get secret noise 1, right? So we record that. Then General Marshall gets on and makes a call. With the same white noise record, they make a mistake or something. We get secret noise 2, right? And so now, if I'm an attacker, I take secret noise 1 and I subtract secret noise 2. And what I end up with is these two cancel each other out. And then what I end up with is like Eisenhower's voice and then like the negative of Marshall's voice. In technical terms, this would be like an XOR operation, right? You'd end up with Eisenhower XOR with Marshall, and then you can do all kinds of attacks to try to break it, right? So you can just check common English words because you're pretty close to the plain text at that point. You just check common English words until you get something, and then kind of decrypt as you go, or just listen to it. Probably be fine with this example. So that's what a nonce protects against. A nonce basically guarantees that each of these is going to be unique, even though you're using the same secret key. Each kind of message primitive is going to be different, and you don't have this problem. Okay, so now we get to the actually interesting question, which is what if you want to accept messages from anyone, right? There are a lot of you here I've never seen before tonight. Like, what if you wanted to send me a secure message? We have no way of coordinating ahead of time. I have no way of sending you a one-time pad. I don't want to send you a secret key because then you have my secret key, and you can use it to decrypt messages that are sent to me. So it's kind of a tricky coordination problem, right? Like, I can't tell you a key right now because everyone else would hear it. So this is the problem that public key cryptography was designed to solve. So basically how this works, let's imagine Alice and Bob are chatting. Cryptography is two most famous individuals, Alice and Bob. So Alice generates a secret key. Usually this is random bytes with some kind of math done or some kind of qualifications done on what exactly can be in the secret key. And then from that secret key, you compute a public key, which is a set of mathematical transformations on the secret key. Bob does the same. And then we share our public keys. So we only share the part of the key that's public. Keep the secret key very secret. And then Alice computes that we have a function f, right, that we have to define later. Alice computes f with Bob's public key and her secret key. Bob computes f with Alice's public key and Bob's secret key. And these produce the same value, right? Like that's kind of the magic trick of public key cryptography is that f with these two different keys produces the same integer value. And then you can use that for symmetric encryption. Now that we've agreed on a key, we can do symmetric encryption with each other in a stream cipher, like the one I showed on the last example. So so that's kind of the magic of. I thought this was really cool that like we can agree on a number even though we haven't shared all the information with each other, right? And obviously there's math involved in how to do that. So the key math is you need f with that magic property, right? Where like you can do that transformation, right? Like that's obviously important that it enables the whole operation. And the other thing that you need is if you have a public key, you shouldn't be able to reverse it and get the secret key. So that's another property of how you're generating these public keys is that you need to make it hard for them to be reversible. Okay, so broadly this is called public key cryptography. The specific version of public key cryptography or flavor of it is called Diffie-Hellman, named after the two people that were the primary inventors of Diffie-Hellman. We're going to walk through like a super simple example of how this works, just to show how like you get this kind of secret key. So we picked two numbers, p, which we're going to be doing a bunch of modular arithmetic and multiplication with, and g, which is the base for exponentiation. P should be a prime number, but right. Don't use numbers this small for your crypto system. It's probably going to be pretty easy to break, but apart from that, you can use anything. Okay, so now Alice, how does Alice do this? She picks a random number, doesn't matter, could be anything, and gets modulo 37 of that number. So she picks 87, mod 37 is 13. Is everyone familiar with modular arithmetic? Okay. And then once you have that secret key, which is 13, you generate a public key, which is g raised to the 13th power, and then also modulo 37. So 5 to the 13th power, modulo 37 is also 13. That's just a coincidence that those two keys happen to be the same. In hindsight, I should have ran the random number generator another time to get a different number, but bear with me here. Okay. There's no guarantee, right? Like that doesn't, okay. Bob does the same. So Bob picks 106 for his random number. He gets 32. He raises 5 to the 32nd power, runs it through modulo 37, and gets 9. So Bob shares his public key, which is 9. Alice shares her public key, which is 13. And then, so this is Alice. So Alice is using Bob's public key to generate S1. So she does 9 raised to the 13th power, modulo 37 equals 12. And then Bob does the same. He takes 13, which is Alice's public key, raises it to the 32nd power, which is his private key, modulo 37, and gets 12. So now they both have the same number, even though they haven't shared one of the pieces of information that they need with each other. And you can imagine this with extremely large numbers on the order of 32 bytes and lots of modular arithmetic and a large modulo factor, and that is the basics of public key cryptography. A fun fact is that this technology was actually, you could not export it outside of the United States throughout the 1990s, which I'm not sure if any of you had to deal with, but, oh, interesting. Okay. Yeah, I'm kind of curious how that worked, like whether they would check your laptops at the security gate or.
We ignored it.
Oh, okay.
We had it on a T-shirt. This T-shirt is illegal to export.
Exports are close.
Interesting.
The algorithm was not a munition. A computer that had the implementation of the algorithm on it was munition.
Interesting. Okay.
So like Game Boys were munitions, not being exported.
That's really wild. Anyway, it's not illegal anymore. You can fly around.
Yeah,
and obviously, browsers are using this technology at the heart of every like TLS transaction that you do.
But if you found one of the old Game Boys, it's a fun fact, not for export, it's class 3 computing munition.
Interesting. So yeah, so that's a pretty trivial example, but it's hard to reverse. If you're given the public key of 13 and you're asked to find the secret key, this is the math problem that you have to solve. 5 to the 8th power, right, where a is some secret number, equals 13 mod 37, right? Or 5 to the 8th power mod 37 equals 13, right? Solve for a. This is not easy to do. In fact, one of the like. One of the most common ways that people try to brute force this is just by like increasing the value of a until you find it, right? Like there's no real secrets to do this besides get a quantum computer. It's conjectured to be like hard, right? Like I think it's not proven, but it's conjectured that like solving this is known as a discrete logarithm problem. Like finding a is really hard, especially when the numbers get big and you're not using 37 as your modulus for this. Example. So now I imagine this is Whitfield Diffie. I imagine him like doing the world's worst bar trick where he's like going around at a bar and trying to pick up people by like asking them to pick a number, any number, and then going through the whole elliptic curve cryptography and showing that you can get the same secret key. And then saying, like, is this your number? You know, at the end of it, like a magician would do. Anyway, you probably didn't do that, but I thought it would be funny. Okay, so now let's get to the paper. Curve25519, new Diffie-Hellman speed records is the headline. People were most interested in the speed. TLS used to be slow. It's gotten a lot faster, especially now. It's coupled with things like HTTP2, but it was a big concern for a very long time that encrypting things was too slow, and so you needed to use plain HTTP because it would take too long and it would use too much CPU time. So obviously, anything that sped up doing public key cryptography made it easier to deploy HTTPS and save CPU resources and saved server compute capacity. So people were pretty interested in it for that reason. But there are some other nice benefits that I want to explain. The paper's by Daniel Bernstein, who also wrote libsodium. He's been very influential in the cryptography community and in some of the papers that he's written and published over the last decade or so. Okay, so why would you want to use this, right? Or what was so groundbreaking about this? Let's talk about it. So one is misuse resistance. It's hard to misuse this curve. In some ways, the other curves, you have to be careful in how you configure them and set them. As an example of misuse resistance, which way does the store open, right? Does it open in or out? You can't really tell from looking at it which way it goes, right? You might have to push, you might have to pull, it's not clear. Slides to the sides, right? You have to push from the bottom and it kind of goes up in like a dog door. So which way does this door open, right? It's pretty clear, you push on it. You can't pull, there's nothing for you to pull. So in terms of misuse, it is harder to misuse this door, right? Than the other one. And this can actually have really tragic consequences. So this is a photo of a place called Victoria Hall. In the 1890s, they held a kids show at Victoria Hall. They had about 2,000 kids. And some point towards the end of the show, the magician who's up on stage says, okay, we're giving out free toys. And his aides start handing out free toys up at the stage. And all these kids in the upper decks start rushing down the stairs towards the lobby. But there's a door to the lobby. The lobby door opens inward towards the stairs. So all these kids are trying to run down the stairs, and the door opens inward towards them. On top of that, the door is bolted, so only one child can pass through at a time. So basically, like, all these children rushing down, there's no way for them to get back out. There's a stampede. A lot of them were trapped and crushed. So speaking of misuse, right, like these things, if you make them easy to design, then you can prevent a lot of problems like this, right? So that incident was actually pretty critical in passing legislation that led to these doors getting installed in public auditoriums throughout. That was in England, but similar incidents in the U.S. led to crash bars being installed throughout the U.S. and sort of mandating that this technology would be widespread, right, to prevent stampedes or to give people a safe outlet in the event of stampedes.
That was Kurt Klein.
If you're interested in this topic, there's a book by Don Norman called The Design of Everyday Things. I highly recommend it for anyone in any field, especially in software. We have to design lots of things, interfaces, documentation, readmes, etc., for everyone to use, and you should be thinking about how things are designed, and especially thinking about how to prevent things from being misused or used incorrectly. Speaking of prone to misuse, JWT. So JWT is everyone familiar with JWT? It's JSON Web Tokens. It is a method for basically sending data and specifying which algorithm you should be used to decode or decrypt the data that's kind of in the token. So one of the methods in JWT is a public key. They have a public key algorithm that you can use. However, a lot of the libraries that implemented JWT did not validate the key. And what happens is, it's kind of hard to explain the small subgroups. What happens is when you do modular arithmetic, you can kind of get in a chain where if you start at a certain input and you do the operations that public key cryptography involves, you can get in sort of like a smaller loop, right? So imagine I specify a value, say like 102, and then the server sends me back another value. But then if I send that value back to the server sends back another value. I keep doing that, and then after like 10 rounds, I'm back at my starting point. Then I know that the secret key is only one of these small values. That's the small subgroup attack. I'm not explaining it very well. There's a lot of fancy math involved, but it's a way to basically reduce the space, right? Where a secret key should be like anywhere in 32 bytes or close to it. You can reduce the size of that really, really fast. So JWT, all the libraries that I checked, this is a blog post by Adobe recently, all the libraries that I checked misvalidating that the received public key is on the curve, right? So this is an example of misuse, right, in public key cryptography. So Curve25519, that curve was deliberately chosen to avoid these small subgroup attacks. In particular, this is how you generate a private key for Curve25519. You generate 32 bytes of random data. In the first byte, you AND it with a number 248, which clears the first 3 bits. And then in the last bit, you set only the bits between 64 and 127. So what happens is, if you do the math, the only subgroup that is vulnerable, the only kind of like loop group is 1, 2, 4, 8, those small numbers. But when we clear those bytes, we make it impossible for you to loop through those values. So it's basically the design and the choice of the curve made that problem impossible, made that attack impossible. So that's Oh, I might just talk at this point. Or it's not going on that.
I'll do my best. Battery.
Okay, so next one is speed. So it's kind of hard to explain. This was basically in the implementation of Curve25519. It was not just the choice of the curve that was used, but also the implementation was deliberately chosen. The author figured out a way to make it really fast, to do the math that is involved with computing this curve very quickly.
Am I coming?
No.
It's happened before.
Also, like, since you're interrupted, remember to like repeat.
Turn it on now.
Yeah.
It's in the other room.
Yeah.
All right.
It's like the voice of the God.
Yeah. Everyone listens to what I say. So the floating point math works really well with null registers. That's partly in how the curve is computed and partly in choice of the prime. So this 25519 comes from this prime number, which is kind of integral to the calculation, which is 2 raised to 255th power minus 19, which is a prime number. It's close to, like, the main value in it is close to 2 to the 256th power, which is 256 bits and 32 bytes. All right, great. We're back. Okay, so this computation involves a lot of modular arithmetic, right? So you have to do a lot of modular arithmetic modulo this number, right? If you imagine from this example, I'm dramatically simplifying here, but like this number is 2 to the 255th power minus 19, right? Like instead of 37. That's like the curve, right? Like that's the primary operation, and then you have to do a lot of modular arithmetic here to take other really, really large numbers and mod them with Curve25519. And then also you have to do a lot of multiplication, right? You imagine these two numbers are also huge, and then you're doing modular multiplication on that. And the way that this calculation is involved, you don't want to calculate out this whole thing and then take the mod of it. You kind of want to do it as you go. And the author figured out a way to do that very quickly by sort of splitting the constants into smaller numbers and figure out a way to do the math sort of faster on Intel registers. The third principle that is really valuable in the paper is it protects against timing attacks. So you might think timing attacks are we send two different inputs to the function, and they take different amounts of time, and we use that to determine some data about like how the computation is going, right? So the quintessential example of this is like a password comparison function that exits when it finds a byte that doesn't match. So if you send enough inputs to it, you can kind of guess the password by just seeing how long it takes, averaging that over enough times. If it takes longer, you're closer on the right track, right? So AES and other encryption functions, and a lot of the implementations were not actually constant time. And one of the reasons is that array lookups are not constant time. You might think like indexing into an array always takes the same amount of time no matter where you're looking in the array, but it really depends on whether the array lookup is in a cache line, which cache it's in, whether it's in the L1 cache or the L2 cache, the array that you're trying to index into. Have you just recently fetched this value? There's another paper called Cache Timing Attacks in AES by the same author that goes into this in more detail. Here's just one slide from that paper. AES scrambles a 16-byte input N using a 16-byte key K, one 256-byte table, and another 256-byte table. These are expanded into four 1024-byte tables defined by this matrix where you're XORing the tables and inverting them. So that's a lot of memory, right? And you have to kind of fetch this into cache, and these might be expelled from the cache at different points in the computation. Your computer might start doing different things while you're computing one of these secret keys. So this is a big problem, right? Is that all of the authors, all the implementers of AES assumed that these array lookups would be in constant time, and they weren't. And the author was able to extract secret keys from a different server based on timing these operations, just sending different values and measuring how long they took. Anyway, so how does Curve25519 get around this? It computes values in pairs. So anytime you need to compute like what the value of a byte is, you kind of compute the complement of it as well. And you do that in constant time. So let's say we need to look up x of b, where b is some input dependent bit, right? So like a bit that an attacker can choose to be 0 or 1. So a simple example of this would be you just do the lookup, right? Like x of 0 or x of 1, you fetch the value, right? But that's not constant time. So what you do is you fetch both values, and then you multiply by whatever b is, 0 or 1, and you end up with the final value. So this will always take the same amount of time no matter whether you're searching 0 or 1, right? Like you have to fetch both of them, then you have to do the multiplication by 1 minus b or by b, then you have to do the addition, right? It's slower, but it also protects you against those kind of timing attacks that were common in other cryptographic public key encryption libraries. So the paper ships with an assembly implementation that was actually written in this language called QHASM, QHASM. The problem is if you start with C and you compile down to assembler, you can often get in a situation where you're generating 3 assembler instructions where 1 would do. And that can also screw with the constant time operations, and obviously it makes it slower if you're doing 3 instructions when you could have done 1 instruction. That's going to be slower. So the author wrote an optimized assembler version and shipped that. And it's 16 kilobytes, which is also pretty small in size, which made the library attractive as well. And provided a reference implementation for people who wanted to implement the same version in assembler in other languages. So yeah, so that's it. This is my website. I run my own company. If you're interested in this or other topics, I'd be happy to chat. This is the first time I've given this talk, so if you have feedback on it or want me to come give it at another place, I'd be happy to work on that or help with that. So thanks very much. And that slide link doesn't work just yet, but it will in like 10 minutes. So, thanks very much. Are there any questions? Yeah.
Do
operations that prevent timing attacks have to do with that curve in particular?
Repeat the question.
Oh, so the question was, do the operations that prevent timing attacks have to deal with this curve in particular? I don't think so. I mean, it's possible that a different curve would require more computation in general, but I think it was a lot in the implementation. And frankly, I'm not that strong on the math involved in the paper. There's a lot that I just didn't understand, but it was a lot on like the implementation just made it kind of good no matter which curve you were computing, I think. Yeah.
How is elliptic curve public encryption different from RSA problem?
The question was, how is elliptic curve public key cryptography different than RSA cryptography? And the answer is, I don't really know that well, unfortunately. Sorry. Yeah, I don't know. The keys are a lot smaller is one difference. Oh, okay. So yeah. So that's okay. So yeah. So RSA I guess involves prime factoring, right? You multiply two primes together, and then you distribute that, and then you can break a key if you can figure out what the two prime factors are, but that's difficult. Sorry. Yeah. So I guess I just remembered. Yeah. Elliptic curve is based on that log problem that I said above, where it's like breaking it is hard. The discrete logarithm problem. Yeah. Thank you very much for explaining that. So. And the keys are 32 bytes. RSA, the keys are 1,024 bytes, I think. Yeah.
So this curve solves problems. How confident are we that it doesn't also give the author of the curve access to all of the encrypted stuff by having a class that we don't know about?
Yeah, that's a good question. So how confident are we that the author of this curve did not insert a backdoor or some other method that would let the author only decrypt the information or a weakness in that sense? I don't know. At some point, you have to trust someone, right? It's really, there's a whole theory of security where you want to make everything public. If something relies on a secret, then if you find out the secret, you can break it, right? So systems that sort of rely on some kind of information being secret aren't as reliable as ones where all of the information is public, right? In this case, you can write your own implementation of Curve25519, and this has been analyzed by every major browser vendor and a lot of mathematicians. Basically, the smartest people, right? If there's a problem with it, then hopefully they would have found it, but you don't know, right? So what? It comes from Bernstein, yeah. Daniel Bernstein, he's the author, yeah.
Do we know if anyone has written their own implementation or whether everybody just copy paste?
That is a good question. The question was, do we know if anyone's written their own implementation? I would guess yes. I would say don't use it, but or try to use the try to use the reference versions for the same reason you wouldn't want to build a nuclear reactor in your garage. You might screw it up with disastrous consequences, right? But yeah, I don't know. Sure, yeah. What's up?
Well, I actually asked that to tie into his question of do we trust it? Because if somebody somebody as capable as Bernstein has written it,
yeah,
their own implementation has verified that it's completely compatible, then we have more reason to trust that code. Right. So yeah, so the point is, if there are other implementations they all agree on what the inputs and the output should be, then we're sort of safer. Yes, I would assume that there are independent implementations, especially in situations where you can't use assembler. Probably had to write code. I can show you the Go. The Go version is in golang.org/x/crypto/curve25519. You can take a look there. There's a primitive called box, which is in the libsodium package that uses curve25519 and a stream cipher to encrypt messages using public key cryptography. And I found it to be pretty easy to follow along with. So I want to check that out. Yeah.
How do you quantify the performance? Is there best case, worst case, and given ranges?
Yes. So the question is, how do you quantify the performance? And I think what they do is just measure CPU cycles. And again, one of the goals is that every single input takes the same amount of time, regardless of what the input is. So it should be taking a constant number of cycles. So you can compare on the same machine, you can compare the number of cycles. let me see. I want to find there's this website called. He also put together this website called Supercop. Oh, I'm not on the internet, am I? Oh, there it goes. Okay. Okay. Yeah, it's in the movie. Where is it? Oh, it is? Okay, here we go. Yeah, so it's a benchmarking suite, basically. And I think he just took he and the co-authors, every single implementation they could find and just put them all in a suite and then added instructions that said, here's how you can run these on your own machine. And then output the timings in a common format, and then you can upload them, right? So yeah, it's a contributing computer time to benchmarking. Like you can run the benchmarks and then send the URL to this mailing list, and then they will upload the benchmark. So I think that's how they kind of do that. bench.cr.yp.to is the URL, yeah.
Current applications of this, I believe it's used in Bitcoin. I'm pretty sure it's used in SSH as well. Any other places where it's used that are commonly?
Yeah, so the question was about what are some current applications of Curve25519. Bitcoin, I'm not sure about. It's used in SSH. It should be used when you terminate TLS 1.2. I'm pretty sure it's used to generate public keys as part of that. The newest versions, I think it's also in TLS 1.3, but I would have to double check that. I know, more and more people. I just wrote a library that uses that as the primitive. If you go to github.com/kevinburke/Neckel. You'll get a library that uses that primitive for public key cryptography. And I know a bunch of people are using it to generate public keys on phones and send them around to kind of secure data. Join GitHub today, good. But yeah, anyway, that's up too as well. Yeah.
How would you compare two different implementations to see if they're equivalent? You just do alterations on each one to make sure that they match up.
That's a good question. How would you compare two different implementations? I don't know. I guess I would just try to just sample random private keys. Obviously test that the invalid keys are not generated by either one or valid. But yeah, I would try to just, generate a large random sample and compare the values and see if they're the same. And also compare the timings, right? So you want the timings to always be the same no matter what the input is. So measure the number of CPU cycles and see if there's a big variance in the number of CPU cycles per input that you have. Yeah.
You said that the timing attack that in the previous version that this one commented for, was that theoretical or demonstrated?
Demonstrated. So yeah, so there's a paper called Cache Timings in AES. I think that's the name of it. Sorry. But yeah, so that was, he set up cache timing attacks on AES. Yeah, here you go. So he set up a dummy server with a 16-byte key, which is shorter. And also it relied on a TCP timestamp being generated by the server so that they could get more accurate timings from that other server. But you can still do it. You just need a larger number of samples, right? If you don't have that, you can still do it. You just need a larger number of samples to compute to recover the key. So yeah, I think they fixed those though once this paper came out. But yeah, again, check your CPU implementation in your OpenSSL version.
Do you have any idea what the optimization differences are for Intel versus other chips?
Yeah, the question is, do I have any idea what the timing differences are for an Intel implementation versus the other implementations? And no, I don't. There are notes in the paper. There are notes in, I think, this paper and notes in the Curve25519 paper that are specifically designed for CPU authors, CPU implementators, about here are the things that would be nice for us to have if you are designing a CPU, hypothetically. And here are some gotchas to avoid if you're writing code that uses those assembly instructions. But no, I don't know the specific details. I'd look at this site, Supercop, and check the architectures there, see what people say.
Also, helpful compilers will put the timing attacks.
Helpful compilers will put the timing attacks behind an instruction, right? Yeah.
Okay.
Any other questions? Thanks very much.